Well, hello and welcome again to our journey into number theory, and this very last video of this section on the Riemann Zeta function was going to briefly look at some connections with the Bernoulli numbers and to show that we can use the Bernoulli numbers to find the value of the zeta function at even integers. There are many ways of motivating and defining the Bernoulli numbers. Not all of them are equivalent, so one has to be careful about which way we're going to define them. For our purposes, I'm going to define them essentially as the Taylor coefficients, or the coefficient in the Maclaurin series of t over e to the t minus 1. So this has a removable singularity at t is 0. So it's got a Taylor series or a Maclaurin series, and I'm going to call the coefficients bn on n factorial. So we're going to end up with a series like this, and we want to get our hands on these coefficients. So usual trick one does with this is I'm going to multiply this up to the other side, and I'm going to turn this into its Maclaurin series, which of course looks like this, starting from m equals 1 because we've subtracted off the constant term here. So I then end up with just t equals this, and we can now just equate coefficients on both sides, and that'll give us a nice recurrence. So equating coefficients, we discover that b naught has to be 1, and I'm going to put k plus 1 equals m plus n. If you write all this thing out and expand it out, then the coefficient of t to the k plus 1 on both sides gives you that 0 equals b naught on k plus 1 factorial plus b1 on k factorial 1 factorial, and so on, up to bk on k factorial 1 factorial. So the k's are going downwards to 1, and the 1's are going upwards to k. We can pull out a factor of 1 over k plus 1 factorial and arrive at this sum, and the point of doing that is that then enables us to write these factorials using the binomial coefficients. So that gets me a nice recursive formula here for working out the b sub k's. So if b1 is 0, then this thing here has to be 0, and from this we can compute various values. I often find in practice it's sort of easier to work with this form up here. So for example, we know that b naught is 1, so if I put k equals 1 in, I get b naught on 2 factorial plus b1 over 1 factorial, and the sum of these has to be 0, so now I get b1 is minus a half. And for the next one I just do b2, I put k equals 2 in, so I get b2 on 2 factorial plus b1 on 2 factorial plus b naught on 3 factorial is 0, and then plugging in the previous values we worked out, we get b2 is equal to 1 over 6. Well, however you do it, you can compute the first few Bernoulli numbers, and we get minus a half, a sixth we've just seen. Now when you work out b3 you get 0, b4 is minus 1 on 30, you discover then that b5 is 0, b6 is 1 on 42, and so on. Now after you've done a few of these, you begin to realize that once we get past b1, all of the odd indexed Bernoulli numbers are all 0, and so we can write that down as a corollary that once we get for n bigger than 0, once we get past that b1, then all of the odd indexed Bernoulli numbers are 0. The proof of this is actually quite cute. We know b1 is minus a half, so I can pull off the first two terms of the Maclaurin series, and I'll take the minus t on 2 on the other side, and I'll leave the 1 there. Now this function here, if we look at this function f of t is t over e to the t plus t on 2, this remarkably is an even function. I'll leave that that's a lovely little exercise to do. Or what I suggest you do is you just look at f of t minus f of minus t, and believe it or not, when you simplify you get 0, and that'll tell you this is an even function, and that means the odd coefficients up here must all be 0. Now, Bernoulli numbers, the main reason for introducing them here is their connection with the Riemann Zeta function. And this is given by the following theorem, which goes back to Euler, in fact. So it's an old result, but it's a beauty, and this one goes back to Euler. So if t is a positive integer, then just look for the wood for the trees here. You've got some factor times zeta of 2t. So this is giving you zeta at an even integer, positive even integer, and it's connected here with the Bernoulli numbers, b2t, and there's some other factors around it with some pi's and things. So that's a lovely formula which enables us to calculate explicitly zeta of an even positive integer. So the proof of this is a little bit technical. As before, I'm going to use the expansion for cot x, which comes out of complex analysis, in fact. So this series arises from complex analysis. You can look it up in books. It's an expansion for cot x, which is 1 on x minus twice this infinite sum. And if we multiply by x, both sides, just to get rid of this 1 over x, I get an x squared there. And if you look at this term in here, and think about geometric series but backwards, then this term here, this x squared on n squared pi squared minus x squared, this is the sum of a geometric series. And so I work backwards and write down what series it's the sum of, and it turns out to be the sum of this series. It's just the common ratio is x on n pi squared, and so we can rewrite this then in this form, and the point is then we can then pull the n to the 1 over n to the 2t out into this series, and that's just zeta of 2t, and then we're left with the sum from t going from 1 to infinity of this expression. So there is one way of writing this this x cot x. On the other hand, one can write cot x again using complex numbers. We can write cot x in this form, which is just of course the cosine over the sine in complex form using complex exponentials. And so again, multiplying by x gives me this expression, and I can multiply top and bottom by e to the ix. And I'm going to split this up then. I'm going to write this as in this form. So I'm really going to write this as minus 1 up the top, and then add 2. And then I can do the division, and that gives me this expression plus this. And this one is, remember, that's how we define the Bernoulli numbers, except I've got a slight change of parameter here. So I'm replacing the t with 2ix, and I can expand this out as its Maclaurin series using the Bernoulli numbers. And remembering that the bs's are all 0 if s is odd, except for the first one, and we've taken care of that here. So I can replace the s with 2t and arrive at this form. Now, if we then equate the coefficients of x to the 2t in our two expressions so we've got this expression and we've got this expression, and if we simply equate the coefficients of x to the 2t for t positive in the expressions for x cot x, that gives me this formula here, and that's what we wanted to prove. The result now follows. So you can now calculate zeta of 2n, where n is a positive integer. So zeta of 2, of course, I'm sure you know, is pi squared on 6. That was the famous result that Euler first discovered. He also discovered that zeta of 4 is pi to the 4th on 90, z to the 6th is pi to the 6th on 945, and so on. And so so zeta of every even integer is some even power of pi times some coefficients, and the coefficients, of course, are connected back with the Bernoulli numbers. I leave it, it can be shown, tutorial problem, or you can look it up in a book, that zeta of 1 minus 2n, that is, these are at the negative odd integers, because remember, at the negative even integers, zeta takes the value 0, the so-called trivial zeros, but at the negative odd integers, it can be shown that the value of zeta is minus b2n on 2n, which is a lovely simple formula. So, for example, then, zeta of minus 1 is minus a 12th, which you can plug it in. Zeta of minus 9, for example, is minus b10 on 10, which is minus 132. Little is known about zeta of 2n plus 1, that is, what happens for zeta at an odd positive integer. These remain a great mystery. They're numbers of some sort, of course, but we don't really understand them very well. We don't even know whether they're all irrational. Apery in 1979 proved that zeta of 3 was irrational in a rather interesting and controversial, I might say, proof. More recently, this was 2001, Riemann proved that zeta of 2n plus 1 is irrational for infinitely many n. One would assume it's irrational for all n, and that at least one of these numbers, zeta 5 up to zeta 21, is irrational. There may have been some further work done since then, but I'm not aware of it. But certainly this question about trying to understand zeta at these odd positive integers is very mysterious. I finish with just an asymptotic formula for beta of 2n. We can rewrite this lovely formula we had connecting zeta of 2n and the Bernoulli numbers. We can take the absolute value of both sides to get rid of the minus 1 to the n term. And now we can use Stirling's formula, Stirling's approximation for n factorial, which says that n factorial is asymptotically root 2n pi n over e all to the n. And I can use that to replace this term up here, so I plug that in, replacing n with 2n in our Stirling approximation. And just tidying up and rearrange gives me this expression. Now, zeta of 2n, of course, looks like this, and as n goes to infinity, so asymptotically this is just going to 1, and so for very large n then, this is approximately 1, and I can multiply up and I get this lovely asymptotic formula for the Bernoulli, certainly the even Bernoulli numbers. Or rather, the Bernoulli numbers evaluated at positive even integers. It was, so this is an interesting factor here. It was shown by Leeming in 1989 that this is in fact less than 5 times root n pi n over e pi to the 2n for n bigger or equal to 2. Just a couple further comments about the Bernoulli numbers. They turn up in lots of different places. They're very, very interesting. A prime number is said to be a regular prime if it does not divide the numerators of these even indexed Bernoulli numbers up to p minus 3. This is a rather perhaps a strange definition for a prime to be regular if it has that rather strange property. It doesn't divide the numerators of these numbers, but when Kummer was working on his attempted proof, which failed sadly, of Fermat's last theorem, Kummer was able to prove that Fermat's last theorem was true for all regular primes. But of course there are infinitely many irregular primes, and of course the Fermat's last theorem took a lot longer to finally be proven. Another connection with another little application of the Bernoulli numbers is in the summing of, which is why they were named the Bernoulli numbers, because the Bernoullis were interested in finding so simple formulae for finding the sums of nth powers of x. And it turns out that this, you can sum x to the n, x equals 1 to k minus 1, by using this formula here. This sum, this is a finite sum of course, connected with the Bernoulli numbers. For example, if I want to find sigma x squared from x equals 1 to k minus 1, then I just write out this sum. There it is. Plug in the numbers. That's what comes out when you work out there the binomial coefficients 1, 3, 3. And you've got a third out the front. And when you put the numbers in and simplify it, it comes out to this, which is that well-known formula. Similarly, you can also show, for example, doing the little exercise to show that the sum of the cubes is given by that. And I leave you to have a look at the sum of the fourth powers and so on using the same formula. That's the end of this chapter. In the next chapter we're going to start looking at the prime number theorem.